Let's suppose you had the chance to see the most advanced civilization in the universe. What would you see? What would they look like? Would they have some kind of music? Or how advanced would their science be? A civilization that advanced would probably already have technologies we do not even dream about yet. Things like Dyson Spheres, or travel at speeds very close to, if not greater than, the speed of light. They probably achieved total control over space and time. Those words sound like magic, and maybe they are for a civilization we cannot picture. But even magic, if it exists, would show up on a power meter somewhere. Some control over space-time is not a separate currency from joules. It is what joules buy when the bill is big enough. It is due. That limitation is not a small detail. It is the starting point of the whole problem. Every organism that has ever lived on Earth is descended from one same last common ancestor, called Luca. We are not sampling the menu of possible biologies. We are looking at one dish that happened to work on one planet. Life here spent a long time in water before it spent time on land. And that history is written in our senses. Our eyes see visible light because water is transparent to visible light. Submerged beings needed that window. A civilization born in methane clouds or under ice 10 kilometers thick might build intelligence on chemistry we would not recognize as a face. They might sense magnetic fields the way we sense color. They might communicate in pressure waves through an ocean we would call a moon. None of that changes the Kardashev question later. It only changes the costume we keep trying to draw. Evolution on Earth also teaches a humbling timeline. Complex animals are recent, agriculture is recent, industry is a blink. If the universe is 13.8 billion years old, and the sun is 4.6 billion, then there was time for many Earths to run the experiment before us. Some may have reached 0.9 and stalled. Some may have hit type 2 and gone quiet. Some may never have left the ocean. The ladder does not care about our vanity. It cares about what's accumulated over time. So when we ask what the most advanced beings in the universe look like, we are secretly asking a harder question with bad data. We are projecting our one evolutionary road onto every planet in every galaxy. Maybe that is why the question feels both exciting and empty at the same time. Exciting because the universe is huge, empty because our imagination keeps drawing humans with different makeup. The mistake is not that we wonder. The mistake is assuming the answer must look like a character design sheet. Civilizations are not species portraits. They are patterns of energy used, stretched across time. Science fiction keeps giving us faces because faces are easy in a movie. Kardashev gives you something harder and more honest. He gives you a budget. A budget tells you what a civilization can build, even when you cannot see the builders. A budget tells you whether they can melt ice caps on purpose or only by accident. A budget tells you whether they can send probes across a galaxy or only across a continent. That is why this video pivots from faces to joules. Joules are the only universal language we have evidence for. But here is the turn that saves the video from becoming pure guesswork. We may not know what the individuals look like. We may not know their music, their jokes, or whether they sleep. We can still know what the civilization is capable of, because capability leaves footprints bigger than bodies. And the footprint we are going to follow in this video is energy. Let me make that less abstract. I, Pedro, am one person on Earth. You are one person on Earth. Forget us for a second. If aliens wanted to understand human civilization without meeting any of us, what should we show them? Not a selfie, not a resume. Show them the International Space Station orbiting above the atmosphere. Show them the Great Wall stitching mountains together. Show them a dam holding back a river the size of a province. Show them a city lit from space like a circuit board. They would not learn our names. They would learn that something on this planet learned to reorganize matter and energy on scales no animal can manage alone. That is why the examples I gave earlier were not random tourism photos. The station needs orbit, the wall needs quarry and logistics. The dam needs a river held back by concrete poured, with machines powered by fuel. Each image is the same sentence written in a different material. The sentence is, we learn to spend energy on purpose. Scale is the part humans forget, because we live at human scale. The IS weighs hundreds of tons and circles Earth every 90 minutes. The Three Gorges Dam displaced rivers and people and still only captures a fraction of the Yangtze's kinetic budget. A night map of Europe from space is not art. It is a heat map of coal, gas, nuclear, and wind translated into photons for our eyes. Aliens would not need to land in Paris or Sao Paulo. They would need to integrate the glow and ask what engine feeds it. That is macroarchaeology. That is the Kardashev instinct before Kardashev had a name. When astronauts look down at night, they do not see faces. They see coastlines traced in light. That pattern is the macro portrait Kardashev wants you to notice. Wants you to know, not Pedro, not you, the grid. That macro view is the whole trick. Archaeologists do not need to meet every Roman to understand Rome. They read the roads, the aqueducts, the coins, the ash layer. We are about to do archaeology on civilizations we have never met, using stars instead of pottery shards. And the first clue on every site is the same one that runs through human history: how much energy the builders could put to work. The history of humanity is the history of energy conversion. Fire to cook, animals to pull plows, wind to grind grain, steam to move factories, oil to move cars, uranium to split atoms. Each step felt like the final word to the people living inside it. And each step was just the next rung on a ladder that keeps going. We split atoms to light a bulb at home, but the honest timeline starts with bombs. Progress and danger have always shared the same engine. Notice how each transition rewired society, not just machines. Fire let humans stay awake after sunset, which changed storytelling and planning. Draft animals multiplied muscle. Windmills turned geography into profit wherever the air moved. Steam turned coal seams into cities. Oil turned deserts into kingdoms overnight. Uranium turned physics into geopolitics. None of those transitions were gentle. All of them were energy transitions wearing different costumes. When Kardashev sorted civilizations by watts, he was sorting the deepest layer beneath the costume. That engine is why a civilization that burns wood to heat food sits lower on the ladder than a civilization that uses electricity to heat food, run computers, charge phones, and cool cities. Not because wood is shameful, because the second society commands more joules per second for more purposes. Energy is not one technology among others. It is the permission slip for everything else. No surplus energy, no surplus future. Wars over oil were never really about oil as a liquid. They were about who got to aim the joules. The Industrial Revolution was not a vibe shift. It was a step change in how many watts a square kilometer could spend per year. When historians mark eras, they are often marking energy transitions without saying the word out loud. An astrophysicist named Nikolai Kardashev understood that in the 1960s, and he was not writing science fiction. He was a radio astronomer in the Soviet Union trying to answer a practical question. If another civilization exists, how loud would its signals have to be for our telescopes to hear them across light years? To compare loudness across worlds, he needed a ruler. He built that ruler out of energy. He also argued that between 1 gigahertz and 100 gigahertz, the interstellar medium is relatively quiet, a window where a loud civilization might punch through cosmic noise. That band is still where many SETI searches start. The scale and the search were born together. Radio astronomy in the 60s was young and loud with discovery. Quasars had just shocked the field. Cosmic microwaves were fresh news. Kardashev worked in a culture that took space seriously as engineering, not only as poetry. His scale was a way to turn philosophical arguments about aliens into numbers you could plug into an antenna equation. How many watts do you need at Alpha Centauri for us to hear you? How many watts at the galactic center? The scale made the Fermi question quantitative before the phrase great filter existed. In 1964, at the Bayurakan conference in Armenia, Kardashev published a paper whose title translates to Transmission of Information by Extraterrestrial Civilizations. The famous scale was a tool inside that paper, not a poster for the internet. He sorted civilizations into 3 types by how many watts they could wield. Type 1, near the technological level of Earth at the time. Type 2, able to use the full output of a star. Type 3, able to use the energy of a galaxy. The numbers are staggeringly far apart on purpose. He was not measuring fashion. He was measuring broadcast power. Type 1 in his original paper meant something close to Earth's consumption in 1964, about 4 trillion watts. Later writers moved Type 1 to all sunlight hitting the planet, near 10 to the 17th watts. The goalposts moved as our ambitions grew. The logic stayed the same. More watts, more story you can tell across space. The same year, on the other side of the Cold War, Frank Drake pointed a radio telescope at 2 Ceti and Epsilon Eridani for the Ozma project, the first modern SETI. Listen. No signal came back. That silence did not kill the idea. It proved how weak a Type 0 civilization sounds when it tries to shout across light years. Kardashev and Drake were asking complementary questions. Drake asked whether anyone is talking. Kardashev asked how loud they would have to be for us to notice their economy, even if they never say hello. Carl Sagan later smoothed the ladder because the original steps were too far apart to describe a species still climbing. His formula is K equals the base 10 logarithm of P minus 6, all divided by 10, where P is power in watts. Plug in humanity today at roughly 20 terawatts, and you get 0.73. We are not Type 1. We are Type 0.73, still on the bottom floor, arguing about the elevator. The beauty of Sagan's tweak is that it turns a staircase into a speedometer. You can watch the needle move as grids change. If fusion works, the needle jumps. If we stagnate in fossil fuels, the needle stalls. If a war burns cities, the needle can twitch down. The scale becomes a diagnostic tool for a species, not a trophy case for galactic emperors. That is why 0.73 shows up so often in conversations about the future. It is not a rank, it is a vital sign. Sagan called that phase technological adolescence, and the name stings because it fits. We can split the atom and still fail to feed everyone. We can map the cosmic microwave background and still burn coal. Adolescence is having power without knowing where to aim it. Kardashev's scale does not judge moral. It reads the meter. If that feels unfair, notice that hospitals and hurricanes both run on the same currency. The scale only asks how much currency exists, not whether you spent it on music or missile. Notice what the equation says without mercy. What matters for placement on the scale is energy spending, not kindness, not art, not how many languages you speak. Watts per second. Energy is not love. Energy is capacity, and capacity has a ceiling in physics. Hypothetically, the most a civilization inside our observable universe could spend is the energy of that observable universe. People extended the idea to multiverses in types 4, 5, and 6. Type 4 would eat an entire universe. Type 5 would eat multiverses. Type 6 would live outside space, time entirely. Kardashev himself treated those as improbable thought experiments, and the physics gets cruel fast when you push on them. The observable universe is not everything that exists. It is everything we can ever receive a signal from, because beyond a certain distance, space expands faster than light, and the horizon runs away from you. To harvest another universe, you would first need to reach it, and reaching it may require more energy than exists inside your own bubble. Multiverse physics is not packaged for engineers yet. That is why the serious conversation stays on types 0 through 3. They are already absurd enough to keep us busy for millennia. Types 4 through 6 are useful as guardrails. They remind you the ladder does not stop at galaxy scale unless physics stops you. A Type 4 civilization in some extensions would harness the power of all stars in the observable universe, roughly 10 to the 46th watts in popular estimates. Type 5 adds multiverses. Type 6 exits spacetime. Find two entities, 2, 2, 2, 2, and these bod 2, 2. Kardashev never demanded we worship those rungs. He gave us 3 that connect to searches we can run tonight. When YouTube thumbnails put Type 6 on the poster, they are selling mystery. When WISE scans mid-infrared, they are doing homework. Fair. We still have enough trouble describing types 1, 2, and 3 without leaving the rail. Type 0 is the world before the grid. Hunter-gatherers burning wood, farmers using oxen, sailors catching wind. When every whale and every forest fire is also a Type 0 economy in a sense, because the energy is not engineered, only harvested. Humanity lingered in that band for most of its history. The spike you see on graphs is recent. That spike is why Kardashev matters now and not in the Roman era. Rome was impressive. Rome was still Type 0 by modern accounting. We are the first generations who can read the meter and know we are not at the top. So let us warp the 4 rungs we actually use: 0, 1, 2, and 3. 0 is life with almost no harnessed energy. 1 is a planetary civilization using all the energy available to its world. 2 is a stellar civilization using all the energy of its star. 3 is a galactic civilization using all the energy of its galaxy. 0 is not an insult. It is the default state of biology. Every fish and fern runs on scraps of sunlight or chemistry until something clever learns to hoard jewels on purpose. We are still closer to that beginning than to the end of the ladder. Even with smartphones in our pockets, 0.73 means we are past the campfire and far from the planetary finish line. Earth intercepts on the order of 10 to the 17th watts of sunlight. We use about 10 to the 13th watts. We catch a tiny fraction of the flux that falls on us, and we still struggle to do it cleanly. Moving from 0.73 to 1.0 on Sagan's scale is not a 27% improvement. It is hundreds of times more power because the scale is logarithmic. Each decimal is a multiplier, not a decoration. Type 2 lives near 10 to the 26th watts, the full output of the sun. Type 3 lives near 10 to the 36th watts. A galaxy. We live near 10 to the 13th. The gap between us and Type 1 is not a little more recycling. It is a different relationship with the surface of the world. Think about what 0.73 feels like from the inside. We already live in a world of satellites, particle colliders, and cities that never sleep. From orbit, we look impressive. From the scale's math, we are still rounding error on the planet's sunlight budget. Most of the joules that hit Earth bounce back into space unused. Most of the joules we do use still come from fossil sunlight stored in rock, not from the live flux falling today. That is why the decimal matters. It is not shame. It is accounting. What would Type 1 actually mean for daily life? It would mean treating the planet as one machine with one energy budget. Solar across deserts, wind across coasts, tides timed like train schedules, geothermal tapped with geology in mind, fission where it makes sense, fusion if we ever tame it, all feeding a grid that behaves like circulation instead of a patchwork. The original Portuguese script listed them plainly: solar, wind, tidal, geothermal, fission, fusion, every channel Earth offers. Type 1 is not picking the prettiest source. It is integrating all of them because the planet is one bank account. Weather becomes something you plan around and sometimes plan for. Oceans become storage. The question stops being whether we can afford to turn the lights on and starts being whether we can afford the heat left behind when everything is on. Borders start to look temporary when your power plants orbit the equator and your food grows under artificial suns at the poles. Type 1 is not everyone getting a bigger car. Type 1 is humanity behaving like one species with one engine room. At Type 1, you also stop treating disasters as local tragedies and start treating them as grid events. A hurricane is not only wind, it is a joule delivery system that can knock out regions if your infrastructure is fragile. A drought is not only sadness for farmers, it is a failure of water, energy coupling in a world that desalinates at scale. Climate models become as important as military maps because the enemy is entropy-wearing weather. That sounds abstract until you remember we already fight over rivers and coastlines while we are not Type 1. The fights get bigger when the stakes are planetary. That heat is not a footnote. It is the price of Type 1. Fusing hydrogen into helium releases energy, and seawater is full of hydrogen. A Type 1 Earth would mine the chemistry of the planet itself, including the hydrogen in the sea, for fusion the way we now mine ancient sunlight for oil. The center of the Earth would not be a horror movie setting. It would be a furnace we finally account for on the balance sheet. Volcanoes are not just disaster. They are reminders of the wattage sleeping under our feet. Today we treat geothermal as a niche headline. A Type 1 world treats the planet's interior the way we treat the gas tank, carefully, constantly, with models that update every season. We are not there. Fusion still lives in experimental halls like ITER, where magnetic bottles the size of buildings try to convince hydrogen to act like a star. Every year fusion stays on the horizon is another year. We stay near 0.73 while the climate meter keeps ticking. Researchers who model the climb put Type 1 somewhere between the 23rd and 25th centuries, depending on whether fusion arrives, whether renewables keep accelerating, and whether we stumble into wars that eat the budget. Mikio Kaku once said 3% growth could get us to Type 1 in a century or two. Other papers say that is optimistic. Everyone agrees on direction. They argue about potholes. Fusion is the mean technology of Type 1 because it promises star physics on a planet. Fusing hydrogen from seawater would change the geopolitics of energy the way oil did. except the fuel is everywhere and the ash is helium. The engineering is brutal. You need temperatures beyond 10 million Kelvin, confinement tighter than any jar we have built, and materials that survive neutron rain for years. ITER is not a power plant yet, and for war. UN power low, and English sage, and Kamen's foresize. It is a rehearsal. Rehearsals matter because they tell you whether the next decimal is engineering or fantasy. Right now, the honest answer is both. And potholes can kill a climb. Using all the planet's energy raises waste. No matter how clean the source looks, fusion is cleaner than coal. But thermodynamics still collects attacks. Machines heat up, cities heat up, planets heat up. Type 1 is not a fairy tale where efficiency hits 100%. Type 1 is a civilization that learns to manage its heat budget the way it manages its power budget. If it fails that lesson, it never reaches the star. That failure mode is not science fiction. It is the weather report. There is a second pothole besides heat, physical space. A Type 1 world still has one surface, one ocean volume, one atmosphere. You cannot grow population forever on a finite sphere, even if your reactors are perfect. At some point, the question is not, can we generate enough watts, but can we house enough minds without crushing the ecology that keeps the machine alive? Some researchers argue that near Type 1 technology makes those problems manageable, with orbital habitats and precision agriculture and closed-loop industry. Others reply that every previous century said the same about the next invention. And here we are at 0.73 with extinctions in the rearview mirror. Both can be true. Technology can help. Technology can also accelerate the cliff, which is where Type 2 enters, not as a new topic on a list, but as the answer to a deadline the sun already printed. In about 5 billion years, the sun becomes a red giant. Long before that, any species that plans in million-year chunks asks a simple question: why let most of a star's light escape into empty space when you could catch it? Freeman Dyson wrote that question down in 1960, inspired by Olaf Stapledon's Star Maker. He did not imagine a solid shell. Physics would collapse a solid shell. He imagined a swarm, countless collectors in orbit, an artificial forest of panels eating photons before they vanish into the dark. The red giant deadline is not tomorrow. It is the cosmic version of a retirement account. You start saving early or you panic late. A species that reaches Type 1 and still lives on one planet is betting everything on one star's mood. Type 2 is diversification. Type 2 is putting your civilization's savings into orbit where the atmosphere cannot drown it. That framing makes Dyson swarms feel less like vanity megastructures and more like insurance. That is a Type 2 civilization, stellar civilization, not because everyone lives on a golden disk in a meme, because the energy economy of an entire solar system revolves around the star, the way our economy still revolves around burning old sunlight stored in rock. Rockets, farms, factories, habitats, computers, all fed from the same central fire. Dyson's detection insight was elegant. A star wrapped in industry should look dimmer in visible light and brighter in infrared, because work always leaves heat. You would not need a greeting, you would need a thermometer. Industry always exhales. The exhale is infrared. Dyson bet the surge on that exhale decades before we had satellites good enough to scan galaxies for it. Imagine the politics of that economy for a second. Not because politics is the point, but because politics follows Joules. Who owns the panels closest to the star? Who gets the night side of the swarm? Does Earth become a museum, a park, or a quarry? Type 2 societies might look feudal from the outside, with trillion-ton assets orbiting a common sun. They might look post-scarcity from the inside, if scarcity was always about energy and energy became abundant. We do not know. We know the physics of catching photons is friendlier than the physics of sharing them fairly. Building the swarm is the part that breaks human intuition. Spread Jupiter's mass into thin panels, and you have material to intercept a serious fraction of the sun. The project takes centuries or millennia even for a patient species. That sounds impossible until you notice the sun gives you 5 billion years before the red giant chapter. A civilization that survives its own adolescence has time. Time is the hidden input in the Kardashev equation nobody prints on the slide. Some popular timelines put Type 2 thousands of years after Type 1, not millions, if growth stays exponential and politics cooperates. That optimism assumes we do not trip on the filter between rungs. It also assumes self-replicating robots or asteroid mining at industrial scale, because lifting every panel from one gravity well by chemical rocket, is a joke at stellar scale. Type 2 begins when the star becomes the grid and the planets become the quarry. Stellar civilizations also change where life lives. If you are wrapping a star in infrastructure, you can live on the infrastructure. Habitats inside the swarm, colonies on captured asteroids, farms fed by concentrated starlight. A society could ride its Dyson swarm for billions of years, roughly until the star dies, which is the same time scale as the star itself. That is not tourism in space. That is moving home from the planet's surface to the engine room, because the engine room is where the watts are. Gerard O'Neill and others sketched rotating habitats long before Dyson swarms went mainstream. Cylinders kilometers long, cities under artificial suns, populations in the millions with agriculture in the walls. Those designs looked like science fiction in the 1970s. Under Kardashev, they look like Type 2 urban planning. Said for Douay, if Earth becomes a nature reserve or a museum at Type 2, the real city moves to where the panels are. Kids might grow up without a sky that is blue, only a sky that is engineering. Engineers have also imagined moving the star instead of only wrapping it. A Shkadov thruster is a giant mirror that pushes a star by its own radiation, like sailing on photon. A Type 2 civilization that can build collectors can think about rearranging orbits over millions of years. Type 2 is not only more electricity, it is real estate and trajectory. Robert Bradbury later asked what a star-sized computer would look like. Nested shells like Russian dolls, each layer computing with the heat of the layer inside. That idea belongs here, not as a detour, because Type 2 power and Type 2 thinking converge. Once you catch a star's light, simulation universes, uploaded cities, billions of years passing inside, while centuries pass outside. The Matryoshka brain is what Type 2 energy buys when engineering stops building roads and starts building thought. Bradbury named it in 1997 after nested Russian dolls because the design is literally shells inside shells. The hot inner layer computes near the star. Each outer layer uses the waste heat of the one below. The outermost shell radiates near the temperature of deep space. A Matryoshka brain is a star turned into a thinking furnace. Much of the trouble with processors today is heat. Data centers already drink rivers and exhale hot air because computation and energy are married. A civilization that solves Type 2 power solves the electricity bill for thinking at civilization scale. Clusters of star-sized minds could chew on problems we cannot even phrase yet, including how to jump from Type 2 to Type 3 without tripping over your own waste heat. That idea connects directly to one of the strangest questions in modern philosophy. If you can simulate minds cheaply with stellar power, why colonize galaxies with rockets? Maybe the most advanced civilization never leaves home. Maybe it builds a perfect inside and lets the outside go quiet. Maybe we are inside someone else's semester project. There is no proof. There is a straight line from Kardashev Type 2 to the simulation debate, and that line is made of joules. Nick Bostrom's simulation argument is often quoted without the energy footnote. Running a convincing universe for billions of simulated minds is not a coding problem alone. It is a power problem. A Matryoshka brain is the hardware spec the argument secretly needs. If Type 2 is achievable, simulation becomes cheaper than rockets. If simulation becomes cheaper than rockets, the Fermi paradox gets a new suspect, not extinction. Indoors, the civilization never left because the inside was good enough. That story is unsettling because it fits the silence we see, and because it fits human tendency. We already prefer screens to camping. Once you accept stellar engineering as a consequence of survival rather than vanity, Type 3 stops looking like a random bigger number and starts looking like logistic. If you can eat one star and you live long enough, why stop at one star? A galactic civilization controls energy on the scale of hundreds of billions of stars, not by visiting each one with tourists, maybe, but by repeating the same stellar trick across the disk until the galaxy's light budget changes shape. Building a Dyson swarm around every star in the Milky Way is not a weekend project. It may require dismantling moons and planets for raw material, mining entire solar systems the way we now mine coal seams. Connect those swarms with Matryoshka layers, and you get a galaxy that computes as it shines or dims, depending on how much starlight industry eats. Galactic civilization also solves problems that sound like science fiction until you read them as energy problems. Communication across light years, transport between arms of the spiral, maintaining millions of worlds without each one freezing in isolation. A Type 3 society has enough watts to run relays, accelerators, and habitats at scales that make our internet look like two cans on a string. Kardashev's original paper already guessed that even one Type 3 civilization in our local group would flood the sky with information we might detect. Type 1 whispers, Type 3 shouts in watts. One of friends. Light speed delay alone makes galactic civilization a problem in patience and memory. A message from one arm to another may take 100,000 years. You cannot run a galaxy like a chat app. You run it like a library that updates slowly, with local copies and long-lived institutions that outlive individuals. That is where Matryoshka brains and von Neumann probes stop being curiosities and start being infrastructure. If minds can run slow or fast depending on substrate, a Type 3 builder might think in million-year plans the way we think in quarterly reports. We are bad at imagining that mindset because we die too quickly. The scale assumes you fixed mortality or made peace with deep time. At the center of the Milky Way, Sagittarius, a star, sits quiet most nights, but accretion disks around supermassive black holes can outshine entire galaxies when they feed. That process converts up to 40% of mass into radiation, far better than fusion in stars. A galactic builder might treat those engines the way we treat hydroelectric dams: dangerous, central, and absurdly productive. Roger Penrose imagined feeding stars into black holes on purpose. Quasars already run that experiment without asking permission. A Type 3 civilization is not inventing new physics. It is franchising physics we already photograph. Penrose also proposed extracting energy from rotating black holes with what people now call the Penrose process. Stealing rotational energy from the ergosphere, combine that with von Neumann probes and galactic logistics, starts to look less like magic and more like a supply chain written in general relativity. We are not building it next week. We are naming the parts, so the ladder has handholds. John von Neumann proposed self-replicating machines that could cross space, copying themselves from local materials. You do not need faster than light travel to colonize a galaxy if you can mail factories that build factories. A probe moving at a modest fraction of light speed could cross the Milky Way in millions of years. That is long for a human life. It is short for a species that already survived Type 1 and Type 2. Patience becomes infrastructure. Self-replication also connects back to the simulation question in a sneaky way. If you can copy factories across space, maybe you copy minds across substrates. If you can copy minds, maybe you stop sending meat across light years and send software instead. Type 3 might not look like a fleet of ships. It might look like a packet storm of probes and brains updating each other every 1,000 years. We would not hear hello, we would hear static with structure. But a question hangs in the air before we leave Type 3. If a Type 3 civilization existed right now in our galaxy, would we be able to detect it? The answer Kardashev's logic suggests is yes. Such a civilization would leave marks, especially energy lost as heat. We detect people at night with infrared cameras because warm bodies glow in a band our eyes miss. Galaxies full of industry should glow the same way at larger scale. Dimmer in visible starlight, brighter in mid-infrared waste heat. Detection is not science fiction romance. It is thermodynamics with a telescope. Shouting in watts has a signature. In 2015, the Jihad team used the WISE satellite to study about 100,000 galaxies and ask a blunt question. Is anyone reprocessing starlight into mid-infrared waste heat on a galactic scale? None of the galaxies looked like they were hiding 85% of their starlight inside industry. Some hot galaxies like ARP 220 glowed suspiciously until astronomers traced the glow to star formation and dust, not Dyson spheres at every corner. The result was a null, and nulls matter. They shrink the space where Type 3 builders can hide without telling us nobody is out there ever. The same infrared logic works down the ladder. A Type 2 star should look wrong before a Type 3 galaxy looks wrong. That is why the false alarms we already lived through matter to this story. Since then, the search kept widening. Surveys like WISE and later missions mapped mid-infrared skies with better resolution than Kardashev had in 1964. Each catalog adds another pass where someone asks, does this galaxy look like a factory or like a forest fire? Most look like nature doing nature. A few look weird until someone finds dust. Weird is not useless. Weird teaches classification. The Jihad null is less a funeral for aliens and more a fence post. It says, if Type 3 builders exist nearby, they are either rare, distant, or clever enough to dump heat in ways we have not modeled yet. No results hurt because the same video that makes Type 3 imaginable also makes silence loud. If the galaxy is old and planets are common, where are the infrared footprints? Kardashev built the ladder to search. The search keeps returning natural sky plus our own interference. That gap has a name. People borrow from Robin Hanson, the great filter. Something between dead matter and a galaxy full of engines kills most attempts. The filter might be behind us, meaning intelligent life is rare. It might be ahead of us, meaning power without wisdom ends the climb. The original script asked the question bluntly, could all civilizations that ever existed have gone extinct before reaching Type 1? Not Type 3, Type 1. If the filter sits early, the universe could be full of dead biospheres that almost made it. If the filter sits late, species might routinely invent fusion and still cook their atmospheres. We do not know which story is ours. We only know we are at 0.73 with a warming planet and nuclear weapons on the shelf. The ladder does not tell you which rung kills you. It tells you which rung you are standing on while you decide. But since imagining extremely advanced civilizations is fun, let us step down the ladder on purpose. Kardashev is not only a staircase up, it is also a way to test whether Type 2 signatures are hiding closer than Type 3 ghosts. Most of a solar system's energy already comes from its star. A Type 2 civilization, in practice, is a civilization that has finished capturing that star. Everything else in the system, the planets, the belts, the habitats, runs on starlight that no longer escapes into the void. Stepping down is a method, not a mood. When G-Hat finds nothing at galactic scale, you do not stop searching. You ask narrower question. Does this specific star dim invisible light while glowing in mid-infrared? Does this exoplanet's atmosphere show industrial pollutants? Does this radio band carry a carrier wave too narrow for nature? Each question is Type 2 or Type 1 shaped. Each null result clears a little fog without ending the story. That step down matters because our best false alarms were Type 2 shaped, not Type 3 shaped. We looked at stars whose brightness changed on intervals so precise they felt engineered, like solar panels rotating around a star in a Dyson swarm being built. Then nature offered another invoice. First came the pulsar. Kardashev had predicted regular radio signals could mark advanced engineering. In 1967, Jocelyn Bell found a beat so steady her team joked about little green men. LGM, the beat was a spinning neutron star, a lighthouse made of physics, not alien. Curiosity note, Kardashev himself had described similar signatures in the early 1960s before nature delivered the real thing. Then came the radio burst toward Hardhide 164595 in 2016, announced as a possible technosignature from a known star thousands of light-years away. It lasted about a second, near 11 gigahertz. Follow-ups never saw it again. The best guess became an Earth satellite crossing the beam. Our own machines are loud. Then came Tabby's star, KIC 8462852, dipping in Kepler's data by more than 20%, while volunteers on Planet Hunters watched the flux dance. Each dip was a reminder that irregular shadows are common in astrophysics. Planets make neat clocks, dust makes messy ones. Construction makes messy ones too, which is why the case stayed alive long enough to hurt. Infrared and ultraviolet eventually told a story of grains too small for solid scaffolding. Breakthrough Listen pointed a dish. Radio stayed boring. The star was not building a swarm. It was coughing material into its own sky. In 2019, Breakthrough Listen flagged Bella C1 toward Proxima Centauri, our nearest stellar neighbor with planets. Months of analysis traced it to human radio interference again. Different target, same humility. Those three rehearsals connect because Kardashev's ladder told us what advanced engineering should do to light. Pulsars tick regularly without builders. Satellites tick once without star. Dust dims without intent. The search trains itself by failing in public until the failures become a catalog of natural tricks. That catalog is underrated. Every false alarm teaches a discriminator. Pulsars taught radio astronomers to expect extreme regularity from compact objects. Tabby's star taught exoplanet hunters to model dust clouds with irregular geometry. BC1 taught Breakthrough Listen to cross-check every promising blip against the growing zoo of human transmitters. When the real technosignature appears, if it appears, we will recognize it partly because we spent decades recognizing everything it is not. The lesson is not that the search is stupid. The lesson is that Kardashev's ladder tells you what to look for, not what you want to find. Look for energy budgets that do not close. Look for stars that dim without aging. Look for galaxies that waste heat like factories, not like nebulae. Keep looking, because Type 1 societies may be listeners more than broadcasters. Kardashev said that in 1964, when Ozma already showed how hard it is for a planet at our level to ping anyone across the void, we are still mostly ears pointed upward, hoping someone else paid the broadcast bill. There is another quiet possibility hiding inside that sentence. Maybe advanced civilizations do exist, and they are deliberately quiet. Maybe they learned that shouting across the galaxy invites attention they do not want. Maybe they communicate on channels we have not invented yet, or they moved their minds into matryoshka shells and stopped caring about radio entirely. Silence is not proof of absence. It is also not proof of stealth superpowers. It is data we have not decoded yet, mixed with data we decoded wrong and called aliens first. The zoo hypothesis and the dark forest hypothesis both live in that gap. One says they are watching us like a preserve. One says they are hiding because broadcasting is dangerous. Kardashev does not pick a winner. He gives you a test. If they are quiet but busy, their stars should still misbehave thermodynamically. If they are quiet because they are dead, the sky stays clean. Either way, the ladder turns philosophy into something you can plot on a graph. After that long climb through types 2 and 3, let us step one more rung down to where our feet actually are. Type 1 again, but now as homework instead of fantasy. What if we used all the energy available on the planet, not the star? Earth's center offers geothermal power. The tides offer rhythm. The sea offers hydrogen for fusion. For feet, we would be mining places we barely touch today, extracting jewels from chemistry and geology we currently treat as scenery. That is the civilizational homework assignment sitting between 0.73 and 1.0. Homework is a useful word because it implies failure is possible. Students fail tests. Species fail filters. Homework also implies the assignment is known. We already know where the jewels live. We already know the sun delivers more in an hour than humanity uses in a year. The hard part is not discovery. The hard part is coordination, building a machine the size of a planet without breaking the biosphere that keeps the machine alive. Every climate headline you read is a comment in the margin of that assignment. Some physicists think we could reach Type 1 in about 100 years. Type 2 might take thousands of years if we ever get there at all. The numbers are guesses. The direction is not. Every decimal is paid for in infrastructure, discipline, and luck. Luck is the word we use when we do not want to say catastrophe. A solar storm can fry grids. A pandemic can stall factories. A war can turn cities off. A war can turn. Type 1 assumes you can absorb shocks at planetary scale the way a large ship absorbs waves. We are still a fleet of rafts tied together with cable news. Getting to Type 1 means building the hull, but it is not that simple. And the original script was honest about the cost. Using all the planet's energy increases waste. No matter how efficient the machines become, residue is not a moral failure. It is physics. We already see waste heat and pollution pushing the climate while we are not even Type 1. Fusion would help. Fusion would not erase the tax. Physical space and natural resources are also finite. There is a limit to how many people one planet can carry, even with perfect reactors. Those two problems, heat and head count, can erase a civilization before it reaches the next rung. That is why some researchers ask the ugly question out loud. Did every species that came before us die in that valley? Is that why the sky is quiet? Population math is the quiet cousin of the Kardashev scale. Watts tell you what you can build. Head count tells you who eats the buildings. Isaac Asimov and others warned that exponential people on a finite sphere hits a wall, even if exponential energy does not. Type 1 might solve energy and still lose on ecology if biology outruns discipline. That is not pessimism for sport. It is the same thermodynamics wearing a human face. So we end where we began. You wanted to see the most advanced civilization in the universe. We still cannot paint their faces. We can read their power bill. If they exist at Type 3, they may glow in infrared across a galaxy. If they exist at Type 2, their star may look wrong. If they exist at Type 1, they may be struggling with heat and fusion the way we are now, one decimal at a time, hoping the filter is behind us and not waiting around the next corner. Kardashev gave us a ladder made of jewels. The climb is the plot, the silence is the mystery. The next decimal is the choice still in our hands. Maybe that is the honest answer to the fantasy we opened with. You wanted Dyson Spheres and control of space-time. What we can actually show you is a meter that starts with Lucca and passes through Rome's roads and Hiroshima's shadow and the Is at night, and ends with WISE scanning galaxies for waste heat. The most advanced civilization in the universe might look like nothing our eyes were built to love. It might look like a galaxy that is slightly too warm in the wrong band. It might look like a star that flickers on a schedule we misread as a joke about little green men. Or it might look like us at 0.73, still burning yesterday's sunlight while we argue about tomorrow's reactor. Any of those stories fits the same data until the data gets better. If you made it this far, you already understand the trick. The most advanced civilization in the universe is not a character reveal at the end of a movie. It is a curve on a graph. It is Rome's roads and Kepler's dips and WISE's infrared maps. It is the difference between catching 1/10,000th of your star's light and catching all of it. We are somewhere on that curve, still closer to the campfire than to the swarm, still learning whether silence means loneliness or caution or extinction. Kardashev did not promise aliens. He promised a way to measure ambition against physics that is enough to keep looking up. We will learn which story is true soon enough. The question is, what we do with the answer while we are still at 0.73. Thank you very much, and see you next time.